So now we're going to talk about the weaker interactions, weaker than covalent bonding, between particles responsible for self-assembly. What do I mean by a weaker interaction? Well, a covalent bond may have a bond-free energy of 80 kilocalories per mole. So this means if the attempt frequency for breaking the bond is F0, the actual frequency with which the bond will break is given by this Boltzmann factor times that attempt frequency. And remember, Kt at 300 Kelvin is 600 calories per mole. But this number is a very tiny number. And so almost no matter what this attempt frequency, a bond this strong will never break at room temperature. Let's consider, though, a hydrogen bond, of which more later. For this, the interaction energy is on the order of 5 kilocalories per mole. So then the bond breaking frequency becomes e to the minus 5 over 0.6. And this is on the order of 10 to the minus 4 times F0. So for any reasonable attempt frequency, hydrogen bonds will break frequently at room temperature. Hydrogen bonds are not the only weak kind of bond. This table here shows various kinds of interactions between atoms modeled classically by point charges. The first two are a covalent bond and a charge-charge interaction, which we will ignore because they are very strong indeed, hundreds of kilocalories per mole, tens or hundreds of kilocalories per mole. The first somewhat weaker interaction is the interaction between a dipole and a point charge. Now, what is a dipole? A dipole is any charge separated by some distance. So if we have a charge plus q and minus q and a distance L, the dipole is defined to be QL. The unit is the debye, and 1 debye is equal to 3.3 times 10 to the minus 30 Coulomb meters. Just to give you some reference here, 1 electron's worth of charge separated by 1 angstrom is equal to 4.8 debye's. Water, which is a molecule with quite a big dipole moment owing to charge transfer from the two hydrogens to the oxygen, for water the dipole moment is about 1.85 debye's. Now, returning to what happens to a dipole and a fixed charge, let's make the charge negative, in which case the dipole would like to orient like this. And even although the net charge of the dipole is 0, an attraction is felt because the positive charge is closer to the fixed charge than the negative charge. And as you can see from the slide, the energy of this interaction falls off like 1 over r squared. The next example is a very important one. It tells you what happens if instead of having a fixed dipole, the dipole is allowed to rotate freely around its axis. Now, one might think that this would result in no net attraction, but thermal averaging comes into play here. So this configuration, let's make Q negative, has a lower energy than this configuration. And this difference in energy then means that this state here will occur because of the Boltzmann factor more frequently by a factor e to the delta E on kT. This then results in a net attractive force because the energy is lower in this configuration, and that configuration is visited more frequently because of the Boltzmann factor, and therefore you get an attractive force that in this case falls off as 1 over kT times 1 over r to the 4th. So the next example is two fixed dipoles. I won't talk about that, the result is 1 over r cubed. But let's go now to two freely rotating dipoles. Now the same argument applies there. This configuration for two freely rotating dipoles has a lower energy than this configuration. So for that reason, this configuration is favored once again by a factor e to the delta E on kT, and the result of carrying out the math is that the interaction energy for two rotating dipoles goes like 1 on kT times 1 over r to the fourth. Okay, let's take a look at a few more results. The next topic I want to talk about is molecules that have no dipole at all, but are polarizing. So if we have a fixed charge, let's just draw electric field lines emanating from the charge, and we bring up an atom that is completely neutral, it will polarize to form a dipole. So let's make this plus, put minus on one side and plus on the other, because of its intrinsic polarizability. The dipole moment will be given by the polarizability times the local electric field that it experiences. And the polarizability is given by the volume available to the electrons, and so it has the following units. So for example, for a benzene ring, where the electrons are delocalized over 6 carbon atoms, alpha has the value of about 10, and then times this constant 4 pi epsilon 0 angstroms cubed. In contrast, helium, which is not a polarizable molecule, has a polarizability that's much smaller, of about 0.8 times 4 pi epsilon 0 angstroms cubed. All right, so now let's consider the case of a dipole and a polarizable molecule. So it's neutral but polarizable. The interaction energy in this case falls off as 1 over r to the 6. When the same calculation is carried out for a freely rotating dipole, one gets, perhaps not surprisingly now, 1 over kT times 1 over r to the 6. And interestingly now, if you take just two non-polar molecules and allow for the fact that their own dipole moments can fluctuate because of thermal excitation, one gets this same result, that the energy falls off as 1 over r to the 6. Now, I will just mention that even in the absence of thermal fluctuations, this mechanism still applies, because a completely neutral spherical molecule can get into an excited state where it has a dipole moment, causing polarization of a partner, and it can do this even at absolute zero because of the uncertainty principle. Finally, on this slide, I've got hydrogen bonds, of which we will talk more later. I just want to mention, in connection with the formation of molecules with a dipole, that one very important mechanism is the formation of a so-called Zwitter ion. Many materials, when you put them into a solution, will spontaneously ionize to form a dipole. The molecule still remains neutral. This example here is the amino acid glycine, and what you see is that a proton transfers from this OH group here to this amine group here, forming an NH3, positively charged, and leaving behind an oxygen, negatively charged. This is a very important source of non-bonded interactions that are modulated by the local acid or base concentration of the environment and drive many processes in biology.